Okay, so we're going to talk about the topic in Python, the topic of references to objects. And in Python, everything is an object, including your integers and your floats. So this talk has, as a prerequisite, but not really a strong prerequisite, this talk is going to want you to know primitive types like integers, floats, booleans, and strings, which even though they're called primitive types, meaning supplied by the language, in Python everything is inside an object, so actually even integers are objects. And then I'm going to make some references to some basic data structures like arrays or lists, but you don't have to necessarily know what these things are. Okay, so a little bit of a history. And I've always said in our course that if you know C and C++, C++ is an object-oriented programming language. That's kind of like knowing Latin. If you understand C++ well, you'll understand every concept in object-oriented programming. Okay, so anyway, in a programming language like C, and C++ is a superset of C, so this would also be true in C++, you can make a declaration, integer A, and you could initialize it to a value 1. What would happen in C and C++ is you would get a piece of storage that can hold an integer. You get 32 bits of storage, and we'd have a name A for that piece of storage. Right, so this line would create storage, assign the name A to that storage, and assign the storage value to 1. If you later, in a C or C++ program, this is also true in Java, if you made a new variable B and said B is equal to the value of A, what would happen is you would get a second piece of storage called B. So you have a piece of storage called A, which has the value 1 in, and then you get another piece of storage called B, and this will take this new piece of storage B and take the value inside of A and make a copy of it over in B. So you have A, which is equal to 1 piece of storage, and B, which is also equal to 1. In Python, we don't say the type, we don't say integer. Python figures it out for you. So if you say A equals 1, since you don't have a decimal point, you don't have quotes for a string, and you didn't say true or false, it knows it's an integer. So what will happen is it will create. Oh, by the way, the way you do comments in C++ is 2 slashes. The way you do comments in Python is a pound sign. So comment, so A equals 1, it will create an object, a chunk of storage that is of type integer. It will initialize that chunk of storage to 1. Then, separately, it will create a reference named A and make A refer to that piece of storage. So you might think, what does that mean? Okay? And I have a picture in a second, we'll go over that. Your next line, you're saying B is equal to A. So what Python will do is create a reference to a piece of storage called B and have it refer to the same piece of storage that A refers to. Okay, so pictorially, here's what it would look like. Suppose, for example, we had in Python A equals 1. So what happens? We create a piece of storage, an object, a piece of storage, we initialize its value to 1, and then separate from that, we create a reference called A, and we have an arrow. I'll explain what the arrow, how the arrow is implemented in a little while. A refers to this piece of storage. Okay. Okay, in this example, it's a little different from this example. Now we have a piece of storage B, which is equal to 3. So Python will create a new piece of storage and make it initialize to 3. And then have B a reference to that piece of storage. B now refers to this piece of storage. If we then came along and said, okay, we have a new piece of storage, C, a new variable, C, and it happens to be equal to A. It happens to be equal to the number 1. Python would know, we already have a piece of storage assigned to 1, why make another one? And so what it'll do is it'll make a reference to C, and it'll refer to the same piece of storage from A, from before. If we then say D is a string, and it's equal to spam in quotes, we'll create a string called spam, and then we'll say D refers to that string. So this is a little bit different, and hopefully you don't really need to know this is what's going on behind the scenes, but sometimes you do. This is why I'm going over this. Okay, so what should happen if reference A is assigned to, if we said, okay, A now equals 4. A should equal 4. And another question, what should happen if reference B is assigned to the reference of A? If B refers to A. Okay, so here's the answer to the question. If A is assigned to 4, should we change this 1 to a 4? And if so, what's the consequence of doing that? Well, one of the consequences of doing that is C, which you said was equal to 1, would now be equal to 4 because C and A happen to refer to the same thing, because Python wanted to save a little storage by saying, oh, we already have a 1, let's make C refer to a 2. So what ends up happening in Python is actually if you say A equals 4, and A is currently referring to an object that has a value of 1, we'll make a brand new piece of storage, put a 4 in it, and then A will refer to the 4, so C will still be referring to 1. Okay, and then what should happen if B is referring to A? What would happen is B would no longer refer to the storage of 3, B would just refer to this storage of 1. Now we have this 3 and nothing's referring to it. So that, we'll talk about that in a little while. Is there an issue with having that? Okay, so this is what's going on behind the scenes, and sometimes you have to know that this is happening because it could screw you up. Okay, so a couple of other examples we could look at. So suppose we have a variable A, which is equal to the string goodbye. And then we have B is equal to A. What does that mean? When A was created, we got a piece of storage and filled it in with goodbye, and then we said A refers to that string. B now refers to the same piece of storage A refers to. So now they're both referring to the same thing. Now suppose I come along and I say, all right, B is equal to the string hello. Since we're giving a new value to B, we'll get a new piece of storage, put in the string hello, and we'll have B referred to that, which means A is still referring to goodbye. We're not changing, A would not equal hello because A and B refer to the same thing when we change B, therefore we change A. That's not the case. And then we can print out you say A and I say B. This would actually print out you say goodbye and I say hello. The song about the Beatles. All right. So the point being, even though this line says that B refers to the same thing A is referring to, that reference, A and B sharing the same piece of storage, is not permanent. If you take some later action which causes them to separate, they'll separate. And by changing the value of B, we don't change, anytime we change the value of anything, we get a new piece of storage and set the new piece of storage to the changed value, and then the old one hopefully goes away. Okay, so that's one example. Here's another example. And here's where you need to know, a little bit about data structures. Not very important. But suppose A is an array of numbers, 0 and 1. And then I say B refers to the same thing A refers to. Okay, so we have an array, 0, 1, and B is referring to the same thing. This is a function, append. You can take a piece of storage and run a function on it and alter it. We could say B is equal to B, call the function append and put a 2 on the end. What that does is it takes this list and puts the number 2 on the end. Now you might say, okay, what is A equal to? Well, if A was pointing at the list 0 to 1, and B refers to the same thing A refers to, but now you've altered B, doesn't that mean B is a now separate piece of storage? And the answer to that, this is where Python gets a little confusing, the answer to that is no. And the reason is, we changed B in place. in place means we didn't use a new piece of storage. We took B, which was referring to the list that goes 0 and 1, and we've appended a 2 onto the end of it. So now A and B still refer to the same thing, which is the list 0, 1, and 2. So if we wanted to print out A, it would say 0, 1, and 2, and if we printed out B, it would say 0, 1, and 2. So the difference is, should that 2 be there? Should this 2 be present? Or is, because we said A is just 0 and 1, B refers to whatever A is referring to, then we took the thing that B refers to and we performed an operation on it, and that operation changed B, it appended a 2 onto the end, but it didn't change the fact that A still refers to it. So a little bit confusing. So here's kind of a chart that says, okay, A is assigned to B. So if we say B equals A, that means the content of A is assigned to B. B now refers to the same thing A refers to. The question is, if something else is assigned to B, like B equals hello, that means we get a brand new chunk of storage and B now refers to that chunk of storage and A refers to what it used to refer to. But on the other hand, if we say B is equal to, and we apply a function on B, on the object B, it means the object did not, the object was updated in place, so A still refers to it. So in this case, A does not change, it refers to the old thing it was referring to. In this case, A and B refer to the same thing, B got changed, therefore what A refers to also got changed. So you gotta be a little careful of that. Whenever you change, whenever you do this, B is assigned to A and then you use one of them to alter the object. If you alter the object by not generating a new one, just modifying the existing one, the other reference now refers to the changes you made. Okay. So references to variables, and variables in Python, everything, including primitive types, are objects. So when I say variables, I mean objects, obviously. All right, so we can have a variable A equals the string April 1st, sorry, A1 equals the string April 1st. A2 equals the string April 2nd, A3 equals the string April 3rd. Now I can come along and use an alias. Sometimes it's good to have a variable that is another name for an existing variable. So I could say today is A1. So let's say today is April 1st. So I have a variable called today, and that refers to A1, which is the string April 1st. So it's like today is April 1st. Therefore tomorrow is April 2nd. Now let's say I have software that uses today and tomorrow. It prints out the weather. You know, today is sunny and tomorrow is cloudy. So I want to keep updating today and tomorrow to refer to different days. So basically today, the variables today and tomorrow are just aliases for other variables, right? So now suppose I come along and I say A1 is equal to the string April Fools. So it's no longer equal to April 1, it's now equal to April Fools. This will create a brand new object called April Fools, and A1 will now refer to it. So if I printed out today is and printed out the variable today, it would print out today's April 1, because I changed April 1 to something different from today. And then if I printed out A1, it would say A1 is April Fools, right? So I didn't run a function that modified it, I actually recreated A1, redefined. Okay. Okay, so object references to an array. Okay, so suppose we had an array, A, and it was equal to 1, 3, 2. Then we came along and said B refers to whatever A refers to. And then we said C is equal to, this should have an A in front of it, sorry about that. C is equal to, from index 0 to index 2, I'll change that on the slide. So C is equal to, from index 0 to index 2, whatever A is equal to. So index 0, index 1, index 2. So I'm basically just saying from the first index until I know that it ends on a 2, And then this one I could say D is equal to the array. If I leave out the starting index and the ending index, it says, all right, it knows what the first one is, it knows what the last one is, and does that too. So these are two different ways to, oh, I'm sorry, hold on. This is saying starting at index 0 and then going 2 after it. So C would be pointing to 1 and 3, right? So we're taking everything from 0 until 2, but in Python, if you remember, you don't always use the last one. It's 1 before the last one, right? So this is, I'm creating C by using the first two elements in this array, and I am making an array of 1 and 3. D, I'm making a new array by saying start at the beginning and go all the way to the end, which is really the same thing again, but I'm generating a new version. I'm giving instructions on how to create a brand new array. So C and D will point to two different arrays, but B will not. B refers to exactly what A originally referred to. Okay, so what happens if the sort function is called on A? For example, if we said take the thing that B refers to, which is this piece of storage, and run the sort function, what would that do? It would change this from 132 to 123. And what would happen to A? Well, running the sort function means you change this variable, but you did it again in place. So it's not creating a brand new version of B, it's just performing an operation on the object B using one of the internal functions. So A would refer to the list in now sorted order. So that's why it's important to know this. If someone changed what B is, if you made an array A and you wanted it to stay that way, and somebody comes along and says B is equal to A and then starts playing around with B, they're going to be playing around with A. Okay. All right, so alias to objects. So suppose, for example, we wanted to have an array of information about A's. Let's say we were operating a weather station. So A1 is a list of objects, an array of objects, the day and then the weather. So we could say April 1st, mostly sunny. And then A2 is April 2nd, cloudy. So it's like the day and the weather, right, for that day. Then we can come along and set up an alias. Today is equal to April 1, tomorrow is equal to the variable A2. Okay. Now suppose you came along and you said, I want to change A1 to be a brand new array, April 1, mostly sunny, chance of rain. Today will not have a chance of rain because this is a brand new string. You came out and said, I don't care what April 1 used to refer to, I'm giving it a brand new definition. It's now April 1, mostly sunny, chance of rain. So today, which used to refer to A1, which is April 1, mostly sunny, that piece of storage will stay. Today will still refer to that, but A1 takes on a new value. But what if all you wanted to do was change the forecast for April 1 and append chance of rain onto the end of it, but you would like today to pick up the new value? Because when you print out the weather report, you're going to say, today is this, tomorrow is that. What you would do is you would say, so for example, if you said A2 append a chance of rain, then the variable that tomorrow, which refers to A2, will pick it up because, again, you call the append function. You didn't create a brand new piece of storage, you applied a function to an existing piece of storage, which means it stays the same. Okay. Okay, so yeah, so let me just go back a second. Suppose, for example, we ran a line of code that said C is equal to A. So now the variable C doesn't refer to 1, 3 anymore. C now refers to this piece of storage, the 1, 3, 2 piece of storage. Now, what is this piece of storage? This is a piece of storage that nobody's referring to. None of these variable references are referring to it. So what good is it? It actually has no use anymore. We could never have a new piece of storage refer to it, because the only way you can refer to something that exists is to give its name of something that is currently referring to it. If nothing's referring to it, nothing could ever refer to it again, so we might as well just get rid of it. If you have a piece of storage, and then you start moving around, this one now refers to that one, and this one refers to that one. If this piece of storage ever gets to the point where no variable reference is referring to it, might as well get rid of it. It's just, you're wasting storage, and eventually you could run out of storage. And I go over a memory leak example at the end of these slides. So here's what Python's going to do. If you say x equals a string, and then we'll set it to a long string, and then we say y is equal to x, here's what Python's doing. Python's creating a variable name called x, and it's creating an object whose value is a long string, and then it has a field in it called a reference counter. How many variables are currently referring to it? Okay. So if we ran the line y equals x, that'll create a brand new variable named y, and we'll have an arrow. I'm going to go over what these arrows are in a second. And now two variables, x and y, are both referring to this same long string. Okay, great. Now, so after these two lines are run, this is what your storage looks like. Suppose later on, x is equal to none. That means x is now referring to a different piece of storage. So we'll create a different piece of storage, the value is none, and x will refer to that object, and y refers to what it used to refer to, which is this thing. But as soon as this line of code runs, this new piece of storage is created, x refers to it, y still refers to a long string like it used to, but now we change the reference counts. Instead of two variable names referring to this string, there's one referring to this one and one referring to this one. So every time a new thing refers to us, we increase the count, and every time something no longer refers to it, we decrease the count. If the count ever hits 0, then we have a piece of storage that is completely useless, and we might as well get rid of it. Okay. So there's this thing called garbage collection, where suppose, for example, we have x equals 2,337, y is equal to x. Now x equals 2,338, that means x and y are now pointing to two different objects. And then y is equal to 2,339. We had, when we originally created x equals 2,337, we created this piece of storage. The type is integer, the value is 2,337, and we had x refer to it. Then we said y equals x. We created a name for y and referred to this one. Now we have two things, the count was 2. There were two references referring to this object. Then we came along and we said x equals 2,338, which means we create a separate piece of storage, 2,338, and we say x refers to that one, and y still referred to this one, but we made the reference count drop to 1. Then we came along and said y no longer refers to this one, y refers to a different number, 2,339. So we created another chunk of storage, an integer with the value 2,339, and we had y point at this object, so there's one reference pointing to it. X is pointing to this one, so there's one here. And then the reference count here dropped to 0 because nobody is referring to this. Therefore, we don't need this piece of storage. So every once in a while, Python comes by and says, of all the pieces of storage that you have, are there any pieces of storage where the reference count is 0? And if the reference count is 0, That piece of storage will never be referred to ever again in your program. Might as well free it up to save space. So garbage collection is Python comes around and says, do you have a reference count of 0? No. Do you have a reference count of 0? No. Do you have a reference count of 0? Yes. Then I'm deleting you, because you're pointless. So that's called garbage collection. Okay, so all right, so what is this pointer stuff? So the question is, what is this arrow? How does Python, because computer memory only has numbers in it. So how do you have an arrow if you only use numbers? So the answer is this. Suppose you have, I just did a little cut and paste off of my pie chart. Okay, but anyway, suppose I had a string called string1 equals cat in quotes. And then I came along and said I want to make another variable, string2, also equal to cat. Well, in C and C++, there'd be two pieces of storage both equal to cat, and string1 would point to one and string2 would point to the other. In Python, they say, oh, I already have this piece of storage. You happen to be creating another string that I already have in my memory bank. So I'm going to have string1 and string2 both refer to the same piece of storage. So all that really means is, I'm going to record the name, y, and I'm also under here, there's a box, with the address in computer storage for where this is located. And that's how the arrow is done. So it looks nice, you know, on a diagram you see an arrow coming out, but all it really is one more field that gives the address of where this block appears in storage. And there's a function in Python called ID. If you want to know the address, you can say ID of a variable, and it'll tell you where it's currently sitting in memory. So here's the memory address of string1, and then you do an ID on string2 and get the same exact address. So that's pretty interesting. Okay. All right. All right, yeah, so now just a little bit, we'll close out with a little bit of a history on C and C++. And why, so this sounds very tricky. Why don't they just, if I say A equals 2, why don't they just give me a piece of storage and put a 2 in it and it's called A? Why can't, that seems intuitive. Why are they using aliasing? And if B equals A, then B refers to the same piece of storage that A has. And sometimes if you change A, B gets changed, and sometimes if you change A, B doesn't get changed. It depends on how you change it. Why do we have all this nonsense? And this has to go back to a little bit of history. So, if we have a string A1 set to April 1st, and we have a string A2, a variable A2, set to April 2, and then I decide to make a string called my birthday, and I set that equal to April 1st. Let's say, for example, my birthday is April 1st. So my birthday is an alias for A1. Now my birthday doesn't change. It's not like if it starts raining, my birthday becomes April 2nd. So my birthday should never change. It should always be April. It always should be equal to April 1. In C and C++, you can do this. You can say string, if you say star in front of a variable name, you're saying this is the pointer to a value. And the pointer basically means this. It's the address. The address, the location in computer memory where the thing exists. So in C and C++, I can say string pointer today, and then I could say today is equal to, I wouldn't make it equal to A1. I don't want to say the address is April 1st, but I could say today is equal to, this ampersand means the address of the piece of storage. So here I'm saying today equals the address of the variable April 1. And then from that point on, I could always say star today means the thing that, the piece of storage pointed to by this pointer, I can set it to whatever I want. Now I can change that piece of storage to April Fool's, and both the variable A1 and the thing the object. In C++, you say, in C, you say thing. The thing today points at would also be April. So in C and C++, they realized sometimes you want to have a variable A, gets a piece of storage, and you'd like a separate piece of storage B and say B is equal to A. You would like to get a separate piece of storage for B and copy the value over. Other times you may want to do aliasing. You may want to have two different names for the same thing. So maybe A1 is April 1st, and it happens to be my birthday. So, not, my birthday isn't really April 1st. But let's say it was. Then my birthday could be an alias to April 1, and I never want my birthday to ever switch to another date. So in C and C++, they give you the mechanism to do this. But this got a little bit clumsy, and when Java came out 10 years later, they removed this, because they thought they were giving you too much freedom. They removed it. And so unfortunately, it has to be done some way. Okay, so a couple of other issues. So these are, what I'm basically going over by talking about C and C++ is I'm showing you some of the issues that Python is trying to address by having this confusing naming and referencing mechanism. Okay, so for example, there's the idea of a null pointer, a pointer that refers to a piece of storage that is no longer around. So suppose we said we have an integer, P1 is a pointer, and it equals to, malloc is memory allocate. We can allocate memory. Get a chunk of storage for an integer. So that's what we're asking the storage manager. Give me a chunk of storage for an integer, and I'm going to make P1 point at it. Then I can say, the thing P1 is pointing at is equal to 5. So I'm putting a 5 in there. Then I can make a new pointer, integer, pointer 2. I can now say, pointer 2 is equal to pointer 1. So pointer 2 and pointer 1 are referring to the same piece of storage. So pointer 2 and pointer 1 are both pointing to a chunk of storage that has a value of 5 in it. Now you can call the free function, which says, if I'm pointing at a piece of storage and I call free, I'm telling the storage manager, I don't need it anymore, get rid of it, it's no longer part of my program. If I then try to print out the thing that's being pointed to by P2, I'm going to be printing out storage that's no longer part of my program. So this is called a null pointer. This is where you have a pointer. There should actually be a star in front of here. Sorry, I'll change that. P2 points to, this should be star P2. And it would print out the chunk of storage being pointed to by P2, which has been freed. We freed it because pointer 1 and pointer 2 are pointing at the same thing, and some other person freed up the storage, and then I want to print it out. So you get an error, it's a null pointer error. You're pointing at storage that has been freed up. So I'd like to somehow have this pointing and referencing thing where this scenario could never happen, and that's what the reference count and the garbage collection thing does. Okay, well, what else is in our history? Oh, memory leak. You have memory leaks. Memory leaks won't happen in Python, but memory leaks could happen in C and C++. Suppose we had we wanted to create an infinite loop, so we make a boolean variable called always true, and we set it to true, so it'll always be true. And then we have an integer pointer, P1. P1 points to an integer. While always true, meaning this loop's going to run forever, the thing P1 points at is equal to memory allocate an integer. So just get an integer, have P1 point at it. Get another integer piece of storage, have P1 point at it. So we're going to have millions, this thing's just going to run forever. So it's going to run millions and millions and billions of integers and keep having P1 point at the new one. Well, now we have all these previously allocated integers that nobody's pointing at, and eventually, if you ran this code, it would crash your system because your program would eat up all the memory on the computer system. No other program would have any memory to do anything, and every program would stop. So this was called a memory leak. Very dangerous. But memory leaks can only happen if you're allocating storage and no longer referring to it but it's still around, it didn't go away, and that gets solved with the reference counter. So what would happen here is every piece of storage that we keep allocating over and over and over, P1 will point at it when it gets allocated. As soon as the next one gets allocated, P1 is no longer referring to the previous one. So all the previous ones have nobody referring to it. Therefore, they're pointless pieces of storage, might as well free them up. So if you ran a loop like this in Python, as soon as you created a piece of storage and then created a new piece of storage, the previous one you're no longer referring to would get freed up, and then this would never happen in Python. So yeah, so it's confusing, but there's a point to why it's happening.